we have studied one of the very important heterocyclic compound, six-membered heterocyclic compound, pyridine. Now, in the introduction, we have studied what is meant by pyridine and what is the main source of the pyridine compound. Then also about the synthetic methods of pyridine, means how that compound is synthesized in laboratory. Then also about the resonance effect, means how the delocalization of pi electron is observed in pyridine molecule, how it undergo delocalization, how we get number of canonical structures, and two main conclusions from resonating structures of pyridine. First one regarding electrophilic substitution reaction, and second one regarding the nucleophilic substitution reaction. Actually, the positions 2, 4 and 6, they having positive charge, and therefore nucleophile can easily attack at position 2, 4 and 6 and it undergo nucleophilic substitution at that position, while remaining 3 and 5 position, they are comparatively electron rich, and hence electrophile attack at that position, and pyridine undergoes electrophilic substitution at position 3 and 5. Okay, we have concluded on the basis of the resonating structures. Then we also studied basic nature of pyridine, how it shows basic nature, then comparison of basic nature of the pyridine with pyrrole. Pyridine is more basic than pyrrole, हे यामध्ये आपण स्टडी केलं होतं. And then also about the basic nature of aliphatic amine, alkyl amine, and comparison with the pyridine, means pyridine is the less basic than aliphatic amine. Okay, let us see next point, chemical reaction. First about the electrophilic substitution. Now, similar to other aromatic compound, similar to other heterocyclic compound, this pyridine molecule also undergoes electrophilic substitution. We know that there is a pi electron cloud over and below the plane of ring. Hence, electrophile can easily attack on the pyridine and it undergoes electrophilic substitution. We also studied electrophile can attack on the pyridine at position 3 or 5, and hence it undergoes electrophilic substitution at position 3 and 5. Let us see some reaction. यामध्ये आपण काही reaction study करूया. First one about the nitration. Very simple example of electrophilic substitution. Pyridine, when treated with the concentrated HNO3, nitric acid. Now that reaction is carried out in presence of concentrated H2SO4 at high temperature 300 degrees Celsius. Now what happens here? Here hydrogen atom from the position 3. Hydrogen atom here, each carbon having one hydrogen atom, and that hydrogen atom from the position 3 is replaced by, it is replaced by NO2 group, and we get corresponding nitro derivative, and this particular compound is called 3-nitropyridine. Reaction is a nitration reaction. Pyridine, when treated with concentrated HNO3 in presence of sulfuric acid, we get 3-nitropyridine. Okay, this is an example of electrophilic substitution reaction, and it occurs at position 3. Now let us see next example, sulfonation. Okay, now here also pyridine, when treated with the concentrated H2SO4 in presence of SO3, sulfur trioxide, at temperature 350 degrees Celsius temperature. Now what happens here? Here also hydrogen atom from the position 3. Here there is hydrogen atom at position 3, and that hydrogen is replaced by SO3H group, and we get corresponding sulfonic acid. This is the pyridine 3-sulfonic acid. Now let us see next reaction, halogenation. Again example of electrophilic substitution. Pyridine, when treated with the bromine, and that reaction is carried out at high temperature 300 degrees Celsius temperature, and here also that hydrogen atom from the position 3, it is that hydrogen is replaced by bromine, and we get 3-bromopyridine, and this is example of halogenation reaction. This is bromination of pyridine, and again example of electrophilic substitution. And thus we have studied some examples of electrophilic substitution. One is the nitration, second is the sulfonation, and third is the halogenation. And all these examples are, all these reactions are electrophilic substitution reaction. Okay, next example is the nucleophilic substitution. Actually, aromatic compound does not easily undergo nucleophilic substitution, because nucleophile means negatively charged ion, and already there is a pi electron cloud over and below the plane of ring. Therefore, nucleophile cannot easily attack on the aromatic compound. Therefore, aromatic compound easily undergo electrophilic substitution and not nucleophilic. But this particular compound, pyridine, undergoes nucleophilic substitution. Why it undergoes nucleophilic substitution? Because position number 2, 4 and 6 we have studied in the resonating structure. आपण resonating structure मध्ये स्टडी केलं होतं how the position 2, 4 and 6 that position having positive charge. Position 2, 4 and 6 having positive charge. Therefore, nucleophile can be easily attacked on that position 2, 4 and 6 and that compound undergoes nucleophilic substitution at position 2, 4 and 6. Now let us see general mechanism for the nucleophilic substitution. Actually, what is meant by mechanism? Mechanism means we are going to discuss how the reaction occurs. Each and every chemical reaction is nothing but the conversion of reactant into product. That reaction can be takes place into number of steps. That reaction may be involve formation of some intermediate. That reaction may be involve breaking and making of some covalent bond, and that detailed information about reaction is nothing but the mechanism. Now let us see mechanism of the particular reaction means how the nucleophilic substitution occurs. This is pyridine molecule. Okay, now suppose nucleophile attack on the pyridine. आपण बघूया how the nucleophile attacks on the pyridine. We know that position 2, this is the position 2, and that position 2 is electron deficient. There is a positive charge, hence that nucleophile attack on the position 2. Okay, means nucleophile having negative charge means there is electron pair. Now what happens here? This electron pair, negative charge means electron pair. This electron pair form a bond between nucleophile and aromatic carbon. There is a formation of new bond between that position 2 and nucleophile. Okay, now to maintain the valency of this carbon, what happens? This pi bond undergo breaking. This pi bond undergo breaking and electron pair goes on the nitrogen. Okay, and here that nitrogen acquires negative charge and there is a formation of new bond between that position 2 and nucleophile. We get the intermediate. Okay, this is the intermediate form when nucleophile attack on the pyridine at position 2. This intermediate is resonance stabilized, means it undergo delocalization. Let us see how the intermediate shows a resonance effect. Okay, now here there is a negative charge means electron pair. Okay, nitrogen having negative charge means electron pair. Now what happens? How the delocalization occur? Here this electron pair now form a pi bond between these two atoms. Now to maintain the valency of this next carbon, the pi bond undergo breaking and this electron pair goes on the next carbon and we get the another resonating structure. Now here there is pi bond, here there is pi bond, and now this carbon acquires negative charge. Now there is a negative charge means electron pair. Now this electron pair again undergo delocalization. This electron pair form a pi bond between these two atoms. Therefore, to maintain the valency of this carbon, next pi bond undergo breaking and this electron pair goes on the next carbon. Okay, now here there is formation of new pi bond. While this carbon acquire negative charge, we get the another resonating structure. Here now there is new pi bond while that carbon acquires negative charge. Okay, this is the resonating structure of this particular intermediate. What we are discussing, yes, general mechanism for the nucleophilic substitution. And this is the first step. When nucleophile attack on the pyridine at position 2, there is a formation of this particular intermediate. And this intermediate having a bond with the nucleophile and having a negative charge on the nitrogen. And there is a delocalization of electron pair in the ring, and hence we get number of canonical structure, and thus intermediate is resonance stabilized. Now let us see second step. Okay, this is our intermediate. Okay, this is our intermediate. I have written that intermediate here also. Now this intermediate loses hydrogen. Here there is a negative charge means electron pair. Now this electron pair form a pi bond between two aromatic carbon. Now to maintain the valency of this carbon, this bond between carbon and hydrogen, bond between position 2 and hydrogen undergo breaking, electron pair goes towards hydrogen, it acquires negative charge, and there is a formation of H minus. There is a formation of H minus, means here that hydrogen is removed in the form of H minus, while there is formation of pi bond between these two atoms, and we get the product, and this is the product. Okay, and here now there is a nucleophile at position 2, and this is our desired product. Okay, thus that hydrogen atom from the pyridine is replaced by nucleophile, and we get final product. This is just nucleophilic substitution. But actually, in the second step, hydrogen atom from the position 2 is removed in the form of H minus. But we know that generally hydrogen having positive charge, and it is called proton. But here hydrogen having negative charge, this is called hydride ion. And thus in this reaction, in nucleophilic substitution, there is a removal of hydride ion. From the position 2, hydrogen is removed in the form of hydride ion. We have studied general mechanism for the nucleophilic substitution, means how actually that nucleophilic substitution occurs. In the first step, nucleophile attack at the position 2, we get the intermediate. That intermediate is resonance stabilized, and in second step, that intermediate loses hydrogen, it loses hydride ion, and we get the desired product. This is just about the general mechanism for the nucleophilic substitution. Now let us see some examples of this reaction. First one, reaction with sodamide, example of very strong base. Okay, this is our pyridine molecule. When it is treated with the soda amide, NaNH2 is the soda amide. Reaction is carried out at high temperature, 100 degrees Celsius temperature. When pyridine is treated with the soda amide, what happens? We know that in soda amide, NH2 having negative charge and sodium having positive charge. And here that NH2 minus act as a nucleophile. Now here we know that nucleophile attack at the position 2, and that hydrogen atom from the position 2 is replaced by NH2 group. And thus in this reaction, when pyridine is treated with soda amide at high temperature, hydrogen atom from the position 2 is replaced by NH2 group. We get 2-aminopyridine, and byproduct is the sodium hydride. And this is example of nucleophilic substitution reaction. This interesting reaction is also called as the Chichi-Babin reaction. Name of that particular reaction, interesting name also there. Yes, Chichi-Babin reaction. Okay, when pyridine is treated with the soda amide, we get 2-aminopyridine, and that reaction is called Chichi-Babin reaction. Now let us see next one, next example, reaction with N-butyl lithium. Okay, this is our pyridine molecule. When that pyridine molecule is treated with the N-butyl lithium, NC4H9Li. Okay, this is N-butyl lithium, actually CS3, CS2, CS2, CS2 and Li. Okay, instead of writing that long chain of carbon, I have written only simple molecular formula C4H9Li. This is N-butyl lithium. Okay, reaction is carried out at 110 degrees Celsius temperature. We know that at position there is one hydrogen atom at position 2, and that hydrogen atom is replaced by N-butyl group. That hydrogen is replaced by that N-butyl group, and we get the product. Yes, there is a N-butyl group at position 2, and this is again example of nucleophilic substitution. When pyridine is treated with the N-butyl lithium at high temperature, hydrogen atom from the position 2 is replaced by N-butyl group, and we get the 2N-butyl pyridine. Now let us see next example of the same type of reaction. Reaction with potassium hydroxide, or suppose we can use NaOH, also sodium hydroxide. Okay, when that pyridine is treated with the NaOH, sodium hydroxide at 300 degrees Celsius, we know that in that NaOH, OH having negative charge, means it is nucleophile. And here that hydrogen atom from the position 2 is replaced by OH, and we get corresponding hydroxypyridine. Okay, this is the 2-hydroxypyridine. Then that hydrogen and sodium, it form again NaH sodium hydride. Okay, this is just again example of that nucleophilic substitution. We have studied 3 examples regarding nucleophilic substitution, and first one is the reaction with soda amide. Sodamide, very interesting reaction. Then second one is the reaction with the N-butyl lithium, and third one reaction with potassium hydroxide or sodium hydroxide. How that pyridine react with alkali, and we get corresponding to hydroxypyridine. Okay, this is just about the nucleophilic substitution. Okay, we have studied pyridine molecule in detail. First, introduction, then synthesis of pyridine, how this compound is prepared in laboratory. Then also about the resonance effect in the pyridine. Then basic nature of the pyridine, comparison of basic nature with pyrrole and aliphatic amine, and also about the general mechanism for the nucleophilic substitution. Then some reactions of electrophilic substitution, nucleophilic substitution, etc. This is just about the pyridine. We have studied in detail about that second molecule, pyridine.